So in this class, we will be looking at amplifier as a black box first. So let's say imagine you decided to purchase a component, let's say a microphone amplifier from Amazon, and then you decide to put together a circuit. So I'm going to teach you today how do you build that circuit. So whenever it comes to circuit design, there are three aspects to circuit design. One is you pick out a component, you understand from the data sheet how that component is going to behave, and then later on you build a circuit using that component. First step that you would do whenever you design a circuit is you do some kind of hand analysis. So in the hand analysis or a paper analysis, you would draw a picture on a piece of paper and make some approximations and come up with an approximate idea of how this particular component or the overall circuit is going to behave. That would be your hand analysis. The second thing you could also do is you could use a simulator. For example, Spice, or in Cadence there is a Spectre simulator or HSpice, things like that. So these simulators you can use, and you can put that component in that simulator and do a simulation to understand how this component will behave. Now, in this particular case, you will get a lot more accurate answer because the simulator has modeled everything correctly. And the last step would be you would actually build a circuit on a breadboard or on a bench, as I like to call it, and then you would look at you would put together the proper supply voltage, and you would apply input voltage and look at the output voltage, and you would do experimental verification of your simulation. So think about it again. You do paper analysis or hand analysis, simulation, and then last step is going to be your actual implementation on a breadboard. Now, so this whole process requires a good understanding of how do you take complex things and simplify them for hand analysis first. Because what we want is a zeroth order or first order understanding of how the circuit is going to behave, and come up with some ballpark numbers for gain and any other parameters like input impedance, output impedance, things like that. Or how much current is going to flow, what would be this output voltage, things like that. So this is what we're going to learn in this particular class. This kind of abstraction, I feel, is useful when you do it upfront in the beginning, because as we go along, then you will understand why are we looking at these different components, what are these different types of analysis that we're going to learn. So there are three different types of analysis which we do on a simulator. One is a DC analysis, also there is an AC analysis, and there is a transient analysis. So all these three things we're going to learn. How do you do it, when do you do it, when do you do certain approximations. Those are the things we're going to go cover in today's class. So we're going to talk about amplifier biasing, then DC, AC analysis. Okay, so let's say we purchased a microphone amplifier from Amazon or Flipkart, your place of choice. So initially I will simplify a lot, which means that let's say the amplifier looks like this, and we show it using a triangle. This is the output, this is the input of the amplifier, and this is the supply and ground. So this would be your VDD, okay, and this would be your ground terminal, and this is your output terminal, this is your input terminal, okay. And once you get it, you would like to use it. So what would you do? So obviously one thing is you would look at the number of batteries it needs. So you would connect maybe few cells depending upon what has been asked. So these are like 1.5 volt batteries. Let's say in this case is 4.5 volts. So these are 3 batteries. Okay, so they are connected. So a slight diversion. You have to know what's the voltage coming out of AA or AAA batteries. Okay, as an electrical engineer, you must know it's 1.5 volts. The reason I say that is because I interviewed you so many students, and when I give them a piece of battery, the one that's commonly used, they don't know what the voltage is, and that could be very embarrassing. I'm just emphasizing that you must know what the voltage each battery provides. This is 1.5 volts DC volts. Okay. All right. So in this particular case, we have plus minus, plus minus, plus minus. So this is 4.5 volts we are applying. Now, at the input, we would use maybe a microphone. Let's draw the microphone like this, something like this. And the second terminal is connected to ground. And on the other side, we have a speaker. So the speaker generally has a coil, some kind of coil, and then we will connect it to ground. Okay, and I'll explain how this works. All right, so this is the way the speaker looks like. So now you build this circuit based on whatever is given in the data sheet, and this particular node, which is we call it reference node or ground node. Okay, it's a reference potential 0. So when you're if you have to analyze this circuit, how would you do that? Okay, how would you break it down in small pieces and understand this particular circuit? Okay, so let's take the next step, because every time I have to draw the circuit, and if I keep drawing all these batteries, it will be a nightmare, right? So we generally simplify the schematics, and a lot of things are implicit, assumed. But when you get started, you need to know this is the way the circuit is hooked up. And many times what happens is that you really don't know how the circuit looks like at the top level, and you're only looking at some small segment of analysis, and somebody asks you a big picture question and you have no idea. So that's why I wanted to start from the top. Okay, so this is the way you would build this circuit in the lab, for example. Okay, and this particular node is a common node. Okay, so when we are redrawing this circuit, let's say we would draw it like this. So to make it quick, we just draw the triangle, and then we draw input and output. Okay, and this is VDD, and this is your ground. Okay, now you cannot generally in this particular the top circuit of the microphone, this is a little bit different case. However, typically input, you would apply a AC source. Okay, some kind of AC input, and then you will have some kind of biasing voltage, which is VDC. I'm going to explain all these things to you. And then at the output, for now, we will just connect load resistance, R load. R load being, this is where the output power is being delivered, and this has output, V out. Okay. So when we, so initially what you would do is you would do a DC analysis. So which means you would apply only this DC voltage and only the VDD. Okay, and then you would measure the current which is flowing through your circuit, and based on this particular DC voltage, you will have certain model of your amplifier that you can use to conduct AC analysis. Okay, I'm going to repeat this over and over again. So first shot, if you don't get it, that's okay. So from this particular circuit, you would do simplified AC analysis. Okay, so this would be your AC analysis. This is AC ground, and this is your amplifier, and this would be your V out. Okay, so from DC analysis, what you're doing is you're creating a model, a linearized model. We like to call it small signal linearized model. model of your device or a component, and then using that we can quickly tell how this circuit is going to behave. Okay, so this when you do DC analysis, you would remove your AC input source, which is this one. You will zero it out, and when you do AC analysis, you would remove all the DC voltage sources. Okay, that's what you do. I'm going to repeat this stuff, this process again and again. So bear with me just for a few minutes. Now let's see. So let's say we decide to plot the transfer characteristics of this amplifier. Okay, so the transfer characteristics is going to look like this. I'll explain what's on V in and what's on V out. Okay, so I'm going to exaggerate that a little bit. Let me just first use a different color. Let's use a yellow color, and let's say this is the supply voltage, and this is another supply. This is, let's say, 5 volts I'm applying. Okay, so basically since our supply voltage is 5 volts or 4, on the x-axis I have V in and on y-axis I have V out. So the transfer characteristics, let's say, look like this. Something like this. Okay, so what we do now is we can see that this middle range is where you have high gain. So I'm going to draw a point here. So this is where we would like to operate our amplifier. Something like this. Okay, so even though this is output 0 volts, this is 0 0 and this is 5 volts, right? These are DC voltages. So for the purpose of AC analysis, this voltage will be our AC ground. Okay, so this is also AC ground. Now let's say I apply a small voltage at the input. This is time domain this way, and this is the output in time domain. This is my input in time domain, and this is my output in time domain. Okay, so let's say if I apply a small voltage at the input, which looks like this. Okay, so since we are biased at this particular point in the circuit, then when the input changes, you can see that, for example, let's take one example right here. Okay, you can see something like this. So the output frequency will not change. Frequency should be the same, and you would get something like this. Okay, so we applied a small signal here, small signal input, and here we get amplified input output. And that's what is really going on. Okay, now let's say if we apply a larger signal, then what do we expect? So let's say I apply the same frequency, but let's say I apply a large signal, something like this. Then what you would expect, because if you look here, for example, it's all flattening out, right? So what do you think will happen? I'll give you 10 seconds to think about it. Can you draw the output characteristics that you will see? Okay, I hope you have already traced it, and you would see something that looks like this. okay, purely by tracing the waveform. And you can see that this is where the output is at VDD or ground. So this is highly undesirable because this is called clipping. And this clipping creates distortion. So one good example would be, let's say you take an amplifier or you take a mic, and then you scream into the microphone. Okay, so now for normal input voltage, everything you could listen to it very carefully, very well, and the sound was good. But when you start screaming into the microphone, then you're going to hit the supply voltage VDD or ground of that amplifier in the microphone path. And then when that happens, this particular, the internal voltages would clip to VDD or ground, and then you will hear a lot of distortion, and it sounds like tearing up of a sound. Okay, and that's your distortion. So you really don't want that to happen. So you want to stay in the linear region of the amplifier, so that the fidelity of the sound is maintained. So when we are analyzing circuits, we are generally in this region. Okay, let me show it in the red here. This is what we are trying to do. Okay, so we do a DC analysis. Okay, so the DC analysis helps us to find the operating point of the circuit, which is the red here in this case. So what that means is I have applied an input voltage, DC voltage at this point, and my output DC voltage would be this much, whatever that voltage is. So that would be the DC analysis. And once I do the DC analysis, I will know how much current is going to flow through the device and what is the characteristics of our device. And I can model that particular device with a simple schematic like this. Okay. And the AC signal that we are applying here is actually this AC signal that you are seeing here. Okay, the small signal, and that small signal gives us linear, because around this point we are linearizing the circuit and we know what the gain is, and this is our linearized AC analysis. All right, so the DC analysis and AC analysis helps us find out what the gain of the amplifier is, and we generally call this small signal input analysis or small signal analysis or a linear analysis. Okay, now how do we do this part, which is this blue portion? Okay, now this is since there is a lot of distortion and there is a lot of nonlinearity over here in the transfer characteristics, it's very hard to do a hand analysis. So in that case, we have to do something called transient analysis. And in the transient analysis, as the input goes from one location to another location, we are moving around in this yellow curve, and you are doing you're solving the equations, and then making sure all the laws are followed properly, and you will get the result that looks like this. So using transient analysis, you get very accurate and real-time signal that you would see when you actually put it on a bench, right? Yeah. So let's recap again. What are the different types of analysis that we learned just now? Okay. So DC analysis. So in DC analysis, we find the operating point of the circuit point. So we only apply DC voltage sources, current sources, and then figure out what is the operating point of our amplifier. Okay, and then using that operating point, we figure out what are the small signal parameters of the device under consideration, or the amplifier. Okay, I'm going to go over this one more time, so that then we do AC analysis. Okay, and this AC analysis is essentially a small signal analysis. Around or linear analysis, linearized analysis at operating point.
Okay, and the last one we talked about was transient analysis. Okay, and in this case we are literally doing solving equation. So this is large signal analysis, okay, with exact circuit or device models. Okay, so why are we doing all these things? Essentially, as I explained earlier, we as designers or engineers, we like to do a real quick hand analysis or a paper analysis or back of the envelope analysis, as they like to call it, quickly. And for that we have to. I mean, all we have is a paper and pencil and maybe a calculator, and we should be able to do everything. And for example, if you're doing this in your one of the tests, you should be able to do analysis quickly given certain parameters, right? So this is what we would be doing. We would do the DC analysis quickly, find out the operating point, and around that operating point we can figure out, do a AC analysis, linearized analysis, and we can figure out what the gain is, what the input impedance is, what the output impedance is, and things like that, how much current is flowing, those kind of things. So all this stuff is good when you do hand analysis or a paper analysis. And once you do that, then you kind of understand the circuit at the 0th or first order, as I like to call it. And then we would plug it into a simulator, and we would again do DC analysis and AC analysis because they are really fast. The DC analysis is very quick, AC analysis is very quick on the computer. And then once you are satisfied with that, then we would do the final transient analysis, which takes longer time. Although nowadays the compute power has increased so much that literally all three of them don't take as much time. Okay, but old days when I was designing circuits, we would always do DC analysis, AC analysis, and kind of then at the end of the day when I'm going back home, I would run a transient analysis on the whole circuit. And by the morning when I come back, I would see the results and then kind of try to figure out, hey, now I need to do my DC AC again to figure out a better transient operating point. So, but then gone are those days. Nowadays, the compute power is so good that the transient analysis also doesn't take long time. However, the complexity of the circuits has increased. So you're trying to do the whole chip simulation, and there, the transient analysis could take a long time. However, the transient analysis is the so-called golden truth, because that's where you are satisfying all the equations, okay, whenever you're doing. So somebody only gives you DC analysis and AC analysis, then, yeah, whatever. But then if once they show you transient analysis, I think those results are believable, assuming they have put together circuit correctly. Okay. All right. So now let's take another example. So here I'm going to take a FET MOSFET amplifier, NMOS amplifier. Again, the intent is not to not to complicate the matters for you, but simplify it. Okay, so for example, we are going to do a very simple NMOS amplifier. Okay, so how would we go about this NMOS amplifier? Okay, so we looked up in the data sheet and we decided to purchase one NMOS transistors. Okay, so this NMOS transistor looks like this, for example. Okay, so it has, let's say, 3 terminals. Drain terminal, this is a drain terminal, this is a gate terminal, and this is a source terminal. I know that I have not explained what a NMOS transistor is yet, and we are going to spend a lot of time on that, but that's okay. For the purpose of abstraction right now, what I'm trying to teach you, you can follow this trail of thought, right? So it will have 3 terminals, and let's say we bought this, let me use a different color around it. So this is the thing we purchased, and it has 3 terminals. Okay, and I think all of you have seen what a resistor looks like. So we got a resistor also. So the resistor is in a box, and it has like these colors, different colors, which are representing different value of the resistor, and it has these two terminals. So we connected the resistor like this, okay, and then now we have this is our input terminal. This is what I'm going to connect to ground. Okay, of course I need a supply voltage, so I'm going to connect our battery, and in this particular case I'm going to connect maybe plus minus 1.2 volts, something like this. Okay, so now I'm going to also connect input here, which would be our, as I said again, this is AC input, VAC, okay, which we show with this tilde sign, which is showing like a sine wave, and then we have a DC input, which is we just show as plus minus like this, and it will be, so this part will be coming from your signal generator, okay, and the one on the left side here, and then we would connect this with a wire, okay. So so all these different lines, they are wires, and I think I think it's pretty clear for you, right? Different wires, and we have only two components. We have this MOS transistor, which is called M1, let's say NMOS transistor. We have a resistor which is called R1, okay, and this is our VDD of 1.2 volts. So how do we, this is the way the circuit is hooked up. So how do we analyze this circuit? Okay, so first what are we going to do? We are going to see, we will do a DC analysis from this circuit, right? So what does the DC analysis tell you? So for example, let's say we know that the threshold voltage VTH of this MOSFET is, let's say 400 millivolts. Okay, so if the input voltage is below 400 millivolts, this transistor will be turned off, and there will not be any current flowing through this resistor, right? So we have to apply VTH higher than that. So this VDC input voltage has less to be, let's pick a number. So VDC is equal to 600 millivolts. Okay, so for 600 millivolts of the DC voltage, then we will figure out how much current will flow through this particular device, and for that current, what would be the voltage at this particular point? Okay, because the drop across this resistance will be IR, right? IR1. So now, based on that, we can pretty much tell what this voltage V out at this point is going to be, some DC voltage. Okay. Now, from the V out voltage, the computation of the V out voltage, again, I'm not going into the equations yet. We are going to do that later on, but for the sake of discussion, just assume that we know some DC voltages at the V out based on this 600 millivolts of input voltage and the current. Okay, so this 600 millivolts voltage will give you the IDC that will flow through M1. Okay, and this will give you V out DC voltage. Okay, so once we have this information, then we pretty much know the DC voltages in this circuit. And then we can tell the mode of operation of M1. And let's say the transistor is in saturation region. We are going to learn all these things later on. So saturation region. And for that saturation region, we know how the model looks like of the transistor. Okay, this is what we all know right now. So the DC analysis job is done. We have figured out what the current is going to flow through M1, and the transistor we have determined it's in the saturation region. So once we know all this information, then what do we do? So then we know that we have a model which is for this transistor under this particular mode of operation that looks like this. And I'm just going to again use a first order model. The first order model tells me that the transistor looks like this. This is gate terminal. This is my source terminal. And the transistor looks like a GM times VGS. Okay, and this is our drain terminal. So based on this information, I know the model looks like this, and the value of the GM, this particular current source that you're seeing is a controlled current source. It's a voltage controlled current source, which is also called as transconductance here, GM. Okay. Now this GM, value of the GM is decided by a few things, which is the size of the transistor, okay, and then what is the VGS applied, okay. Now this VGS meaning the DC part, okay, not the AC part. All right. So let's keep the VGS away in this particular because it might be confusing. So let me use the different variable. It depends on the size of the transistor and current. IM1, the DC current flowing through the device. Okay, so these two will give you the value of the GM. And once we have this information, now we would like to draw a AC analysis picture for this particular schematic. So how would we do that? So what you would do then is you would, the rule is as simple as this. First we would, for AC analysis, so we would short all DC or constant voltage sources, okay, not dependent sources, constant voltage sources, remember that, okay. And then what we would do is and then we would figure out basically the model as I said earlier, and then we would put together the circuit. So how is this circuit going to look like? I'm going to redraw again. I'm kind of making it smaller so that it stays in the picture here. Okay, all right. So the model, as I said, was looking like this. Okay. And this is my ground connection. At the input, this is gate, this is drain, and this is our source. Okay. So between gate and source, we have to remove the DC voltage source. Okay, we short all the DC voltage sources, so we would only apply the AC source here, which is the VAC input. Okay, we can call it V in AC, and then at the output we have this resistance R1. Okay, that R1, the other terminal is connected to again 1.2 volts DC voltage source. So we will ground that also. We will short that voltage source to ground. So then the circuit is going to look like this: R1, and this would be ground. So this is we got this node by connecting 1.2 volts to grounded, because this is a DC voltage source. Okay. Okay, so now so this is, we kind of simplified this whole circuit, complex circuit here, to very simple circuit like this. Okay, let's put the values here. This is GM times VGS. Again, this VGS is a small signal value. Okay, and GM is transconductance, and this is a parameter of the transistor. And how did we figure out this parameter? This is figured out from your the current flowing through the transistor, I1, and then also the size of the transistor. Or I mean, it will also have some kind of properties of the transistors, right? So all those things will be rolled into this characterization. Okay, so having said that, what would be our output voltage now? So Vn is applied over here. So now we go back to our Kirchhoff's current law, voltage law, and based on that we can analyze this circuit, and I'm sure all of you can quickly determine that the current flowing through this resistor is flowing this way, so it will develop a voltage that looks like this, and so V out will be equal to, what will be V out equal to? V out will be equal to minus GM VGS times R1. Okay, so what is VGS? VGS is Vn. So V out divided by V in will be equal to minus Gm times R1. Okay, so this is the gain of the amplifier, in which R1 is the value of the resistor that we know, and Gm is the transconductance of this particular transistor, and that is based on where we bias the transistor, and also size of the, or the property, intrinsic property of the transistor based on that. So this is kind of the way you analyze this complex circuit. And what does this sign, negative sign, indicate? The negative sign indicates there is an inversion, which means if I apply a positive going sine wave at the input, then the output will be going like this, okay, with amplification. And Gm times R1 can be factor of 20, 30, 40, depending upon the value of Gm and R1. And that's the way we get amplification. All right. So this is at a high level how we get from choosing a component and putting it down on a breadboard and analyzing it on a piece of paper. So what I just showed you is a hand analysis. Now you could also put this in a simulator, and in the simulator you would pick the transistor, you would plug the transistor, you would put a resistor, and then you would apply the supply voltage and you would simulate the circuit, and it would give you some answer, right? And the reason I'm not introducing simulator right now is because I would really like you to do hand analysis first and then use the simulator to verify your hand analysis. So the hand analysis should be within 10-15% accuracy. The simulator should give you much better accuracy, and of course when you put it on the bench and you measure, that's the ultimate truth, right? So here is a step-by-step process of going from choosing a component, doing simplified analysis like DC analysis, transient analysis, AC analysis, and then actually measuring the device parameter.